Hi Algebra 1 students, this is a video on linear programming. Linear programming is an application of systems of inequalities. So the basic idea of a linear programming problem is that you're given a system of inequalities, which are called constraints. And they're called constraints because they're kind of like restrictions on what x or y can be. And then we also are given a function. So in this case, it's p equals 2x plus 3y. And this is called the objective function. So to solve a linear programming problem, the first thing we're going to do is graph the system of inequalities. So I'm going to start by graphing the line x is greater than or equal to 2. And on my coordinate plane, I'm going to make 0, 0 be the point in the bottom left corner. So I only have my positive x and y quadrant, the first quadrant. So that means that x is greater than or equal to 2 would be, well, there's the line x equals 2. And now I want values of x that are greater than 2, so that means I should shade to the left. Sorry, to the right. So next up I have y is greater than or equal to 3. So I know that's going to be a horizontal line. So if I count up to a y value of 3 and draw in that horizontal line. And these lines are both solid because I have an or equal to symbol in my inequality. So now I should shade above the line because I need y values that are greater than or equal to 3. Next up, y is less than or equal to 6. So that's going to be another horizontal line at 6. And this time I need to shade below because it's less than or equal to 6. And I have one more equation or inequality. X plus y is less than or equal to 10. So this one is actually pretty easy to get into y equals mx plus b form, right? And it would be easy to get the x and y intercepts as well. But I just want to show you one thing here. So I could actually just subtract x over to the other side. And I get y is equal to negative x plus 10. So that's telling me that I have a y-intercept at 10. Oops, sorry about that, guys. So I'm trying to draw on the point at 10. I'm having a hard time. There we go. And then my slope is negative 1. So that means I go down 1 over 1 to get another point, down 1 over 1. And I'm trying to be as precise as possible because it really matters where this line intersects the other lines. Okay, so we get the series of dots. Now I can connect the dots to get my line. And now to decide which way I want to shade, I can plug in the origin 0, 0 and see if it makes the inequality true. So I get 0 plus 0 is less than or equal to 10, which is true. So that means I should shade on the same side of my line as 0, 0, which is down here. And now my graph looks kind of like a lot right now, but the idea is we need to try to identify where are all 4 colors. And you can kind of see all 4 colors in this region right here, right? I'm just going to darken the outline of that region. Okay, so that is called the feasible region. Feasible means possible. So all of the possible x and y coordinates that satisfy our constraints fall within that region. We also have vertices of the region, which are the corners of the shape formed. So the idea here would be is I have a vertice at the point 2, 3. Which is this point right here. My next vertice is at the point 2, 6. Just directly above it. Then if I go over, I also have a point at 4, 6. Right there. Oops. And then my last vertice is at, if I count all the way over to the bottom right corner, that would be the point 7, 3. Now the idea is that I can plug in the vertices into the objective function. So if you see this little table, the x and y values in the table are representing the 4 vertices. And we can plug them into the objective function because the whole point of a linear programming problem is we're trying to maximize or minimize the objective function, and that should happen at one of the 4 vertices of the feasible region. So if I plug in 2 for x and 3 for y, I get 4 plus 9, which is 13. So doing the same thing for the other vertices. Here I should get 4 plus 18, 22. Here I get 8 plus 18, 26. And here I get 14 plus 9, 23. So the idea is that whichever vertice maximizes the objective function, that would be the location of the maximum, and that looks like it's 26. So it means the coordinates of 4 and 6 give us our maximum value of the objective function. And then we can also see the minimum of 13, which occurs at the point 2, 3. So to summarize the relationships going on, it's called the vertex principle of linear programming. So we have this idea that if there is a maximum, oops, let me switch back to the pen. If there is a maximum or minimum value of the objective function, then it occurs at one or more of the vertices, which are the coordinates of the corners of the feasible region. So in summary, to find the maximum, I'm going to abbreviate, or minimum values, you have to plug the vertices into the objective function. And that's what we just showed back here. So if you flip your worksheet over to the back, you'll see 4 problems. And I'd actually like you guys to complete these problems, but I'm just going to model for you what I'd like you to do. So the idea is, given the objective function p, you're finding the maximum or minimum value given the vertices of the feasible region. So if we look at the first problem, I see vertices A, B, C, and D. So A is the point 0, 0. When I plug that into my objective function, I just get 6 times 0 plus 2 times 0, which is 0. So that is clearly my minimum, but I'm looking for my maximum, so I got to keep going. B is 6, 0. So that means I'm plugging in 6 for x and 0 for y. And I get 36. And the idea is you have to keep going and do that for C at 2, 4 and D at 0, 4. And whichever one gives you the largest value for P is the coordinate that maximizes the objective function.